Hello, everybody. Welcome back. My name is Michael. Hope everyone's having a wonderful day so far. I am back on my channel streaming some Python learning independently. And yeah, thank you so much for joining me today. Today is Saturday, the 14th of December, and we are super excited to be getting into more data structures and algorithms in Python. Last night we streamed for quite a while, about 4 hours, and we learned about binary search, and we did a walkthrough of the drawing a ruler like example, going over recursion and the file systems example. So it was a very good session yesterday going over these topics, and we even attempted to implement a binary search algorithm into our actual small business manager project that we've been working on over the past, few weeks. Hey Larry, thanks so much for coming in. Good morning. I appreciate you joining me today. How you doing? I just woke up a little bit ago, got up, got my dog taken care of, and now we're ready to do some a little morning studying here. And yeah, I've got an event this afternoon, so I will be taking a break around 12:30 or 1, and then I'll be coming back for a late night stream to continue the double feature for today. All right. So let's see here. Um, let's jump back into our notes. And where did we end off on last time? I think we ended up right here. We're on 4.3. Recursion run amok. We didn't get 4.2. We'll do 4.1 and 2. 4.2 illustrative examples, and what was it? Analyzing recursive algorithms. Okay. Cool. So let's go down to 4.3 here. Let's let the chat know actually that we are live. Okay. Go. Sounds great. Got that all updated. All right. Let's get into recursion run amok here. Let me take this line here. I'm gonna copy it down here for 4.3. We'll say recursion Okay, let's get into it, guys. Although recursion is a very powerful tool, it can easily be misused in various ways. In this section, we examine several problems in which a poorly implemented recursion caused drastic inefficiency, and we discuss some strategies for recognizing and avoiding such pitfalls. We begin by revisiting the element uniqueness problem defined in page 135 of section 3.3.3. We can use the following recursive formulation to determine if all n elements of a sequence are unique. As a base case, when n is equal to 1, the elements are trivially unique. For when elements n are greater than or equal to 2, the elements are unique if and only if the first n minus 1 elements are unique, the last n minus 1 elements are unique, and the first and last elements are different. If and only if the first n minus 1 elements are unique, the last n minus 1 elements are unique, and the first and last elements are different, as in the only pair that was not already checked was a subcase. A recursive implementation based on this idea is given in code fragment 4.6, named unique 3, to differentiate it from unique 1 and unique 2 in chapter 3. So we have a unique 3 function, which takes in some sort of sequence in the form of s. We have a start and a stop. So if stop is minus start is less than or equal to 1, we're going to return true, meaning that stop would be like 1, start would be 0, less than or equal to 1. Okay, so that meaning if we have one item left, we would return true, because it is unique, right? Elif not unique interesting. Unfortunately, this is a terribly inefficient use of recursion. The non-recursive part each call uses O1 time, so the overall running time would be proportional to the total number of recursive invocations. To analyze the problem, we let n denote the number of entries under the consideration, that is, let n equal stop minus start. Okay. If n is equal to 1, then the running time of unique 3 is O of 1, since there is no recursive calls for this case. In the general case, the important observation is that a single call to unique 3 for a problem size n may result in 2 recursive calls on problems of size n minus 1. Important is that a single call to unique 3 for a problem may result in 2 recursive calls, yes. Those 2 calls with size n minus 1 could in turn result in 4 calls, 2 each with a range size of n minus 2, and thus 8 calls with a size n minus 3, and so on. This would be the worst case. The total number of function calls is given by this geometric summation, which is equal to the power of n minus 1 in prop 3.5. Thus, having a running time of the function unique 3 is O of 2 to the power of n, or an exponential function. This is incredibly inefficient function for solving the element uniqueness problem. Its inefficiency comes not from the fact that it uses recursion, it comes from the fact that it uses recursion poorly, which is something we address in section C, exercise C of 4.11. Interesting. So, an inefficient recursion for computing Fibonacci numbers. In section 1.8, we introduced a process for generating Fibonacci numbers, which can be defined recursively as follows. So f of 0 equals 0, f of 1 equals 1, f of n equals f of n minus 2 plus f of n minus 1 for all values of n greater than 1. So you just add the 2 previous values to find the next value. Ironically, a direct implementation based on this definition reflects in the function bad Fibonacci shown in code fragment 4.7, which computes the sequence of Fibonacci based numbers by making 2 recursive calls in each non-base case. So we have bad Fibonacci. If n is less than 1, we return n, meaning that we return the single value, less than or equal to 1. So if there's no list, we return the list, or if there's a single value or 2 values, we return both of those 2 values. But so else we call bad Fibonacci minus 2 plus bad Fibonacci minus 1. So we call recursive on bad Fibonacci of n minus, computing the nth Fibonacci number using binary recursion. Unfortunately, with such a direct implementation of the Fibonacci formula results in a terribly inefficient function. Computing the nth Fibonacci number in this way requires an exponential number of calls to the function. Specifically, let C of n denote the number of calls performed in the execution of bad Fibonacci. Then we have the following values for the C of n's. Okay, so our first call is 1 of C of 0. We call it again and get 1 again. Our third call to the Fibonacci would result in 1 plus C0 plus C1. Hey, Justin, thanks so much for joining me this morning. How you doing today? I know we just talked a few hours ago, right? If we follow the pattern forward, right, we see that the number of calls more than doubles for each two consecutive indices. More than doubles. Oh, because you have to make 2 calls and 3 calls. 3 calls and 4 calls. So this is 5 calls. This is 7 calls. This is 9 calls. No, that wouldn't be it. That is, C4 is more than twice C2. Okay. C5 is more than twice C3. Oh, in terms of the overall running time, right? Yeah, got you. C6 is more than twice C4. Yeah, and so on. Thus, any calls are greater than n to the power of 2 to the power of n divided by 2, which means that bad Fibonacci n makes a number of calls that's exponential to n. Gotcha. An inefficient recursion for computing Fibonacci numbers. We are tempted into using the bad recursion formula because of the way the nth Fibonacci number, f of Fibonacci n, depends on the 2 previous values. The second most value and the one right before it. But notice that after computing f of n minus 2, the call to compute f of n minus 1 requires its own recursive call to compute f of n minus 2, as it does not have the knowledge of the value of f of n minus 2 that was computed at the earlier level of recursion. That is duplicative work. Worse yet, both of those calls will need to recompute the value of f of n minus 3, as will the computation of f of n minus 1. This snowballing effect is what leads to the exponential running time of the bad recursion. We can compute f of n more efficiently using a recursion in which each invocation only makes 1 recursive call. To do so, we need to redefine the expectations of the function. Rather than having the function return a single value, which is the nth Fibonacci number, we define a recursive function that returns a pair of consecutive Fibonacci numbers, f of n and f of n minus 1, using a convention of f to the negative 1 equals 0. Although it seems to be greater burden to report 2 consecutive Fibonacci numbers instead of 1, passing the extra information from one level of the recursion to the next makes it much easier to continue the process. It allows us to avoid having to recompute the second value that is already known within the recursion. An implementation based on the strategy is given below. Okay. So we have good Fibonacci now, which takes in a sequence n. If n is less than or equal to 1, meaning that some sequence n is less than or equal to 1, return the sequence value and 0. Else AB equals good Fibonacci of n minus 1. So this will unpack So let me go to my whiteboard here. Let's clear out this. Okay, so let's see here. Let's try to draw this out. So if we have some sequence S or N, right? We have 1, 3, 5, 7, let's say. Right? If n is less than or equal to 1, return n return n and 0. So that'll be our base case. Else, we're gonna unpack variables a and b as good and run Fibonacci for n minus 1. Oh, actually, so n would give you. So what is n in this case? Is it a sequence or is it a. No, n gives you the. No, n is giving you the. You want the nth number in a Fibonacci sequence. And because you're just subtracting from n. Okay, so it's not a list then. I'm looking at this wrong. So n, right, is just an integer of like 5. So if we want to, it's saying we want to find the 5th Fibonacci, right? We want to find the 5th Fibonacci. Sorry, I'm using a magic mouse, so this is hard. We want to find the 5th Fibonacci. So what that does essentially is we will load up the number 5 into our first node, right? It will then check if n is less than or equal to 1. Is it less than or equal to 1? No. Oh, sorry. No, it's not. So we're going to go ahead and run the else statement. We're going to unpack two variables, a and b. We're going to run a level of good Fibonacci return a plus b and a. So if we have the first node here is at 5, we call a recursion down for n minus 1 at 4. And what do we return? We return a and b. So I'm not sure what's being given here. What's being unpacked into a and b. Like, so this will become 4, and then it'll run it again. This will become 3. It'll run it again. But what are a and b becoming? Five, 1, and 0 for base case. In terms of efficiency, the difference between bad recursion and good recursion for this problem is likely night and day. I'm not sure what is being unpacked into here. What? Oh, come on. What is... I can't follow what is being unpacked into the variables a and b. So the function good Fibonacci n in recursive means it calls itself with a smaller value of n. A tuple returning. The returning tuple f of n and f of n minus 1, where f of n is the Fibonacci at position n and f of n minus 1 is the one preceding it. Unpacking. The line AB is equal to good Fibonacci n minus 1 takes a tuple returned by the recursive call and assigns a to the first element in the tuple and b to the second. So we have our, let's do this step by step. So base case, when n is less than or equal to 1, we return the value of n and 0. So it would be returned for n equals 0, it'd be 0, 0. For n equals 1, it would be 1, 0. When n is greater than 1, the function calls itself with n minus 1. Good Fibonacci n minus 1 computes the tuple three good Fibonacci computes the tuple big F n minus 1 and big F n minus 2. These values are unpacked into a set. Then it calculates the next Fibonacci numbers. Why is it giving me balloons? What does the balloons do? I don't know what the balloons means. Does it? I'm not sure what the balloons mean. Um, I don't get how is this unpacking two variables? You're returning a plus b and a. A plus b computes the function f of n. The function of f of n minus 1 is plus f of n minus 2. What does the what is those balloons? Let's look up. Let's ask the other instance of GPT here. What are the balloons when streaming on YouTube with OBS? On stream alerts or interactive graphics triggered by events, new subscribers, super chats, new members, likes, or follows. Oh, okay. So if we get a third-party tool listens for YouTube stream events like subscriptions or don't. Oh, interesting. So I think if we get a subscriber, we get balloons or something like that. That's cool. I like the balloons then. Nice. Okay, so I don't understand what is being unpacked here. So if we return Fibonacci 2, hey Moon, I appreciate you coming in this morning. Good to hear from you. And Madi, I appreciate you coming in. Hello, Gina, as well. Thank you guys for joining me today. Good morning to you guys. We're doing a morning study session here. I'm looking at this Fibonacci and I'm having problems with this line of code here. I'm not sure what's being how is this actually being unpacked? Like where are these values A and B coming from? Like I mean, what is being so example for n equals 3, base case of n equals 1. So good Fibonacci is 1, 0. Recursive step for n equals 2. return n equals 0. Return a plus b and a. One plus 0, 1. So n equals 3. It will call the good Fibonacci of n minus 1, which will unpack into 1 and 1. Return those two values. What about a okay, so for good Fibonacci 3, sorry, this should have been for n equals 4. Okay, so I want to see what it does for the 3. So it runs good Fibonacci 3 in the else block. Oh. Okay, so this is challenging, guys. I'm struggling here, not gonna lie. Let's walk through this. So input n equals 4. The first call for good Fibonacci 4, if n condition is equal to 1, less than or equal to 1, we return false. The function proceeds to the else block. Now it makes a recursive call to good Fibonacci 3. Right? Exactly. The second call, good Fibonacci 3. Now it makes another recursive call to good Fibonacci 2. Third call, good Fibonacci 2. Now it makes another recursive call to good Fibonacci 1. So the fourth call, good Fibonacci 1. The condition if n is true. So if n is less than or equal to 1 is true, the function returns the tuple. Returns 1 minus 1 and 0. Back to good Fibonacci 2. The recursive call good Fibonacci 1 return 1 and 0. Oh, so it's going to then unpack 1 and 0 here. Because we called the good Fibonacci function for 1, it's going to return the base case here. And then, like you guys said, it's going to then take a lift off and count back all the way up to our Fibonacci number. Return a plus b. Okay, got you. The tuple is unpacked. We return 1 plus 0, 1, so 1 and 1. Back to good Fibonacci 3. 2 and 1, 3 and 2, 3 and 2. Ah, okay, I get it now, guys. So what's happening here is we will for the whatever value we put into n, whether it be 5, 10, 15, whatever, it will recurse all the way down to the base case. Once the base case is met, we will then return a tuple of the base case. And then we will recurse using our, right, we've been recursing all the way down this whole time. Then it starts to return all of those values up through n. Hey, so this will become 5 minus and 0, giving you the max and the minimum once returned. No, this would give you the base case of 1 and 0. Because Fibonacci would be 1 in this case, because it's less than or equal to 1. So 1 and 0. That would be unpacked in here. 1 and 0, we return 1 and 1. Which gets returned to the original call that we made. Okay. Can you show me tree diagram for this, or a recursive trace? Let's ask it to show us a tree diagram or a recursive trace. Thanks so much for joining me this morning, you guys. It's not the easiest day. Oh my gosh, what is this? This looks like so cryptic. This does not look like what I want. This looks really weird. So we will call good fib and unpack. We call good fib n number of times all the way down until we reach the base case, including the original. Including the original call, right? We need to include that. So we call good Fibonacci n number of times, including the original call, all the way down until we reach the base case, where it unpacks the when it unpacks 1 and 0. Where it unpacks 1 and 0, and then scales back upward to n? I'm not sure exactly. Here's a more detailed explanation of how recursion works. So when you call good Fibonacci n, the function works its way downward through recursive call until it hits the base case. The base case is the stopping condition. When n is less than or equal to 1, the function stops making recursive calls and directly returns a tuple of return n and 0. So good Fibonacci of 1 returns 1 and 0. Good Fibonacci of 0 returns 0 and 0. Unpacking and scaling back upwards. After reaching the base case, The function, quote, scales back up the recursive call. Each recursive call unpacks the tuple returned by the smaller subproblem into variables a and b, using these to compute the Fibonacci pair for the current n. Returns this pair from to the previous level of recursion. So recursion tree for n equals 4, we call good Fibonacci on 4, which then calls good Fibonacci 3, which then calls good Fibonacci 2, which then calls good Fibonacci 1. Good Fibonacci 1 hits our base case and returns 1, 0. Good Fibonacci 2 receives the 1, 0 and computes 1 and 1, which returns 1 and 1. Good Fibonacci 3 receives this value and computes 1 and 1, which returns 2 and 1. Good Fibonacci 4 then receives this tuple and computes the next value and returns 3 and 2. The total number of calls to good Fibonacci is n plus 1, including the original call. Oh, is n plus 1, including the original call. So we have to call it if our good Fibonacci is 4, we call good Fibonacci 5 times. So 1, 2, 3, 4, 5. Oh, you do call it on good Fibonacci 0, and you return 0, 0. Okay, that's why. Of 1. No, but you wouldn't even hit a good Fibonacci 0, right? Because you would hit your base case first. If you have 4 become 3, 2, 1, n becomes less than or equal to 1. Your base case includes the value of 1. So recalling good fib n minus 1 for any value greater than 1 would result in never calling good fib 0. You're absolutely correct. The base case of good Fibonacci function assures that for any value n greater than 1, the recursive call stops at n equals 1 and never calls good Fibonacci 0. This happens because the recursive call in the else block reduces n by 1 each time, stopping once n equals 1. Let's go over the behavior again. We got ChatGPT. We got him. Okay, so we were able to stump the AI here. We were able to prove that it was wrong in a case. It didn't pick up on the fact that our n is actually including the value of 1. It's not saying it has to be less than 1. And so if you think about it, if we have any value of n that's greater than 1, we will recurse down all the way to n minus 1. So we'll go to 2 minus 1, and then we will go and then at that point that would reach our base case of being 1. 2 minus 1 would be 1, which is included in this if statement, so we would return this. Thus, we would never ever return a good Fibonacci of 0 unless specified at the very start of the thing, right? So good fib of 0 would never take place within this recursion unless given as the starting n value. Yes, that's absolutely right. Woo! Okay, I feel a lot better about this. I feel a lot better about the Fibonacci recursion here. So just like someone in the chat said a couple days ago, is that you break it all the way down in some cases, and then it lifts off and goes all the way back up to where it kind of started in a way, right? So what's happening here is the good Fibonacci is being called for n minus 1, so you will return this tuple. Thus, going back up the recursion ladder and returning all these values, right? So I wonder how you would have to draw this though. Like how would we, you know what I mean? How would we go about drawing an example of this? So if we have n is equal to 4, we would start at 4, start at our initial value of 4. We would call good Fibonacci on 3. We would call good Fibonacci again on 2. We would call good Fibonacci again on 1. We meet our case. This returns, at this point, this returns 1 and 0, which gets I'll make these arrows like this, so they show that we are transversing back and forth, returning values to the previous node. So by creating these double-sided arrows in between each node, I'm kind of showing that I can travel back and forth from node to node in this recursion because I'm passing values via this return for each call. So this gets called back to 2, which then does so this gets called back to 2, which then does a plus b and a. So it'd be 1 plus, oh my gosh, this is getting hard. Sorry guys, I'm trying to keep this. 1 plus 1 and 1. Then this gets called and returned back to the third level of recursion, or the second level that we did. So this would be, this becomes 2 and 1, so this becomes, so 2 is our A, so this becomes 2 and 3 here, which gets returned 2 plus 1, right? Which gets returned to here at our n equal 4. And then we would return where is those values? Gets 3 and 2. So you get 1 and 0. Good Fibonacci receives that of 2 and 1. So let me take my, do I have an eraser? Let's get rid of this. Make this bigger. So this becomes 2 and 1. And this receives 3. No, I'm doing this a little bit wrong here, so sorry. Let me back up. I'll put those lines back. So we'll put these inverse arrows back, and then to show that relationship. So the 1 value will return to the 2 value, right? It's not a parallel. It's not a perpendicular return here. We need to go back up the scale. So that's what I was missing in a step. So let me grab my eraser again, delete this, come back here, grab my pen. Okay, so we have this node here down at 1 now, and we are going to return up here, need a smaller size. We're going to return into the second level a value of 1 and 0. We are then going to return into the third level a value of right, 2 and 1. We are going to return to the fourth value, to the fourth level, a value of 3. Oh my gosh. Sorry, guys. I know I need to get like a better mouse. 3 and 2. So then that would correlate to there. Exactly. Boom. That's how it would look. Cool. That makes a lot more sense. Does that help you guys out at all? That makes sense for this explanation? What do you think? Does that help break this down if when I show it visually like this? It helped me, definitely for me, like understand this on a deeper level. Okay. Hey Peyton, thanks so much for coming in. Appreciate you stopping in this morning. Hello. We're doing great. Feeling good. I'm just learning some recursion here. Okay. In terms of efficiency, the difference between the bad recursion and the good recursion for this problem is likely night and day. The bad Fibonacci function uses exponential time. We claim that the execution of the function good Fibonacci n takes O of n time. Each recursive call to good Fibonacci decrease. Oh, hold on. The bad Fibonacci function uses exponential time. We claim that execution of good Fibonacci n takes O of n time. Each recursion call to good Fibonacci decreases the argument n by 1, therefore a recursion trace includes a series of n function calls. Because the non-recursive work for each call uses constant time, the overall computation is O of n time. Maximum recursive depth in Python. Another danger is in the misuse of recursion is known as infinite recursion. So we'll say infinite recursion. If each recursive call makes another recursive call without ever reaching a base case, then we have an infinite series of such calls. A recursive call makes another recursive call without ever reaching a base case. Okay. Then this is a fatal error. An infinite recursion can quickly swamp computing resources, not only due to rapid use of the CPU, but because each successive call creates an activation record requiring additional memory. A blatant example of an ill-performed recursion is the following: def fib and return fib n. So if you'll just constantly return the fib and keep going for fib n. However, there are far more subtle errors that can lead to an infinite recursion. Revisiting our implementation of binary search in code fragment 4.3, in the final case, line 17, we make a recursive call on the right portion of the sequence, in particular going from index mid plus 1 to high. Had that line instead written as return binary search for the original set, this could result. Okay, so not use the use of mid, but return our original search parameters. This could result in an infinite recursion. In particular, when searching a range of 2 elements, it becomes possible to make a recursive call on the identical range. A programmer should ensure that each recursive call is in some way progressing towards a base case, for example, by having a parameter value that decreases with each call. However, to combat against infinite recursion, the designers of Python made an intentional decision to limit the overall number of function activations that can be simultaneously active. The precise value of this limit depends upon the Python distribution, but a typical default value is 1000. If the limit is reached, the Python interpreter raises a runtime error with the message maximum recursion depth exceeded. So we'll say Python has a built-in safety feature capping the depth of recursion at about 1000 and will raise runtime error if exceeded. Cool. For many legitimate applications of recursion, a limit of 1000 nested function calls suffices. For example, our binary search function has olog and recursive depth, so for the default recursive limit to be reached, there would need to be 2 to the power of 1000 elements, far more than the estimated number of atoms in the universe. However, in the next section, we discuss several algorithms that have recursive depth proportional to n. Python's artificial limit to the recursive depth could disrupt such otherwise legitimate computations. However, in the next section, we discuss several algorithms that have recursive depth proportional to n. Okay. Fortunately, the Python interpreter can be dynamically configured to change the default recursive limit. This is done through a use of a module named sys, which supports a get recursion limit function and set recursion limit. Sample usage of these functions is demonstrated as follows. Okay, then we'll say Python's sys module can override this, can dynamically reconfigure the recursive limit with functions get recursion limit and set recursion limit. Right? So then we'll say example, and then we're going to put this Python code here. We'll do the, I don't have the backticks. I need this guy. Python. And then we're going to take this guy. I'll keep the, I like the comments. Import sys. Take this, paste it up here, take this, paste it up here. Okay, and then we need to just close this line of code with these markings, like so, and then if we shift command V, we don't get it. Why? What are we doing wrong? Oh, it needs to be like inside, I think, like that. Now if we were to see shift command view, no. Python why isn't this working? Command C to say for reformat this for mark.md. Copy Paste. Why won't that work? Oh, it's thinking all of this is code for some reason. Why does it think all of this is code? What's going on here? There we go. Something was off there. Okay. Okay, and so then what does that little hash line do? If we have a line between the 4 and the 4.3, it just creates that line. Oh, probably. Okay. What happens if I delete this? Oh, yeah, that line goes away. Huh. Now it's back. Okay. Put one there then. See what that looks like. Yeah. Okay. Cool. All right. Got that formatted. Python's quote sys module. Oh, so if you just do single quotes. So a single tick. Okay, so I need to reformat my keybinds. I need that tick because I have it set to opening my terminal right now. I need that tick. Right, the tick is what does everything. That's tilde. If I go command, no, option. Oh, option, what does the tick? Okay. So what happens if I take, I need to take of the list. No. And what happens if I just go like this? Put a couple of ticks here. Okay, that did solve that one. Why is this a different color? Huh. Okay, let's keep moving here. Further example of recursion. 4.4. 4.4. Further examples of recursion. Okay. In the remainder of this chapter, we provide additional examples of the use of recursion. We organize our presentation by considering the maximum number of recursive calls that may be stated from within the body of a single activation. If a recursive call starts at most one other, so we organize our presentation by considering the maximum number of recursive calls that may be started from within the body of a single activation. If a recursive call starts at most one other, we call this a linear recursion. If a recursive call may start two others, we call this a binary recursion. Okay, so we'll do binary recursion. Binary recursion, and then we have, linear recursion. Then we have binary recursion. Then we have multiple recursion. So if a recursive call starts at most one another, we call this one other. Okay. A recursive call that starts two others. And then a recursive call that starts three or more others. Gotcha. So linear is one or more, binary is two or more, multiple is three or more. Okay. So linear recursion. I'll make these numbers rather than bullets. 3, and then we'll get some space here. So linear recursion. If a recursive function is designed so that each invocation of the body makes at most one new recursive call, this is known as a linear recursion. Of the recursions we have seen so far, the implementation of the factorial function, section 4.1.1, and the good Fibonacci function, section 4.3, are clear examples of linear recursion. More interestingly, the binary search algorithm is also an example of linear recursion despite the quote binary terminology in the name. The code for binary search includes a case analysis with two branches that lead to a recursion calls, but one of those calls can be reached during a particular execution of the body. A consequence of the definition of linear recursion is that any recursion trace will appear as a single sequence of calls, as we originally portrayed for the factorial function. A consequence of the definition of the linear recursion is that any recursion trace will appear as a single sequence of calls, as we originally portrayed for the factorial function. Note that the linear recursion terminology reflects the structure of which a recursion trace, not the asymptotic analysis of the running time. So just like we had shown in our whiteboard here, this was a linear recursion because, as you can see, it went straight down the chain and then worked its way back up the chain. Whereas if we had a binary where it would split into a 2, and then that splits into 2, and those split into 2, and those split into 2, and 2, and 2, and 2, and 2. And so multiple would obviously, if you have like 3 that go into 3, that go into 3, that go into 3, this would be like n to the power, or 3 power, base 3 or whatever to the power of n, rather than 2 to the power of n. So yeah, those are what it's talking about here. It's not talking about runtime, it's just talking about structure of the algorithm, like in a physical sense, right? Summing the elements of a sequence recursively. Linear recursion can be a useful tool for processing a data sequence, such as a Python list. Suppose, for example, that we want to compute the sum of a sequence. s and n integers. Okay. We could solve this summation problem using linear recursion by observing that the number of n integers in sequence s is trivially 0 if n is equal to 0, and otherwise that the sum of the first n minus 1 integers in s plus the last element in s. Observing that the sum of all n is trivially so hold on. Suppose, for example, that we want to compute the sum of a sequence, okay, of s and n integers. We can solve the summation problem using linear recursion by observing that the sum of all n integers in S is trivially 0 if n is equal to 0. So if there are no numbers in the sequence, no, if n is equal to 0, then trivially the sum is 0, right? Meaning that the physical integer is 0 in our sequence. And otherwise, that the sum of the first n minus 1 integers in S plus the last element in S. Computing the sum for a sequence recursively by adding the last number to the sum of the first n minus 1. What? A recursive algorithm for computing the sum of the sequence of numbers based on intuition is implemented in code fragment 4.9. So linear sum takes in a sequence with n integers, returns the sum of the first n numbers of sequence S. Okay, so n is just a physical number that represents an index representation of we're summing up to that index. Plus the n, plus the last value because you're doing n minus 1. So that's why you have to add the last value. Okay, so if n is equal to 0, we return 0, meaning that the value provided is 0. Else return, we want to linear sum the sequence. And then for the value, each time we'll recurse down n minus 1, and we will add to that sequence of the sequence at index n minus 1. Okay, so let's draw this out. So we're starting off with, if we have a sequence and we want to find the fifth sum of the sequence, the fifth sum up to the fifth number, we would say, we would obviously start at our first node here at 5. We would go down to the next node and be at 4. We would go down to the next node and be at 3, down to the next node, be at 2, down to the next node and be at 1, and then down to the next node and be at 0. We have now reached our base case, right? We have now reached our base case of 0, and so we will return 0. So 0 gets returned to here. Okay. Then what gets returned into the next, back up the chain, would be it returns 0. So we'll return 0, but we're also going to return sequence 0 minus 1. Sequence at -1. So that'd be the last value. So then if we go, that would return okay, let's look at this recursion trace here that they show. So we would do the sum of 5. We would do the sum of 4. Okay, 0 gets returned plus sequence index 0. 0 minus 1 would be -1. So you return sequence at -1, right? No, it would be, sorry, if we're at 0, if you're returning 0, you return -1. So it should be 0 plus 4. I'm struggling here, guys. So we would return to the previous level the value of 0 plus sequence at index n minus 1. So if our n at this point is 0, our n would be 1, and we're returning 0 because n minus 1 is 0, which would resemble our n value here when recursed back. So n would be 1, minus 1 would be 0. That would be loaded as n, plus 4 plus 3 plus 6 plus 2 plus 8. Zero plus 4 plus 3 plus 2 plus 6 7 plus I don't get this one. This one's tough, guys. I'm not gonna lie. This is hard. I'm struggling with this one. Okay, we'll copy this and say I'm having a hard time following this recursion. So the linear sum Sn calculates the sum of the first n elements in the sequence. Here's a breakdown of the recursion. When n is equal to 0, the function returns 0 because the sum of the first 0 elements is obviously 0. This is the stopping point for the recursion. Else we return a linear sum with the sequence with an input of n minus 1 If n is greater than 0, the function calls itself recursively to calculate the sum of the first n minus 1 elements of the sequence. Linear sum sequence n minus 1. After that, it adds the nth element of sequence due to the 0 indexing of Python. So if n was 0, if n was 1, we would add the first element in the only element in the list, plus the previous sum that was returned. So 0 was returned. The next element in the list is 4. It was returned down, right? So we return, then 4 gets returned. We add 3 to it. Then 7 gets returned. We add. Why are we adding 6? That's our sequence. Oh, that's our sequence here. So if our sequence isn't in order, this is our sequence. So that's what these numbers are coming from. Okay. So 0 would be returned. We would then add in the value in the list so far, the next value in the list. So it'd be the first value. Then we return that sum. Then we would add to it the next value in the list. That would be 3. So 7. Now we return that. We add the third value in the list. That's 6, 13. Return 13. Okay. Gotcha. Okay, I got you. Reversing a sequence with recursion. Okay. Next, let us consider the problem of reversing the n elements of a sequence S so that the first element becomes the last, the second element becomes the second, and so on and so on. We can solve this problem using linear recursion by observing that the reversal of a sequence can be achieved by swapping the first and last elements, then recursively reversing the remaining elements. We present an implementation of the algorithm in code fragment 4.1 using the convention that the first time we call the algorithm, we do so as reverse sequence 0 length S. Got you. So your stop would be the length of the sequence and your start would be 0, is what we're assuming here. So if start is less than stop minus 1, we go ahead and do the following. So if we have at least 2 elements in our list, so start would be 0, stop would be 5, minus 1, 4, for a total of 0, 1, 2, 3, and 4, for a total length. Got you. So as long as our start is less than the stop, though, it's 1, we can continue, okay? So we'll index into our sequence for the start. We will access that point, so it would be 0. We would then access the last value stop. So the last value in our list. And we set that equal to then we just set them equal to each other. So we just swap them, and then we call recursion on reverse and set increase start by 1 and decrease stop by 1. Okay, this one's cool. I like this one. Reversing the elements of a sequence using linear recursion. Note that there are 2 implicit best case scenarios. When start is equal to stop, the implicit range is empty, and when start is equal to stop minus 1, the implicit range has only 1 element. So stop is 1, and start is 0. We have 0, 0. Okay, gotcha. So we have only 1 element. 0 indexed. In either of these cases, there is no need for action, as a sequence with 0 elements or 1 element is trivially equal to its reversal. When otherwise invoking recursion, we are guaranteed to make progress towards a base case as the difference stop minus start decreases by 2 with each call. If n is even, we will eventually reach the start equals stop case, and if n is odd, we will eventually reach the start equals stop minus 1 case. The above argument implies that the recursive algorithm code fragment 4.10 is guaranteed to terminate after a total of 1 plus n divided by 2 recursive calls to the floor. Since this call invokes a constant amount of work, the entire process runs in O of n time. So we would, for 5 swaps, 3 and 9, then swap, 2 and 8 swap, and then 2 remains, and we're done. And that becomes our new list. Okay. Recursive algorithms for computing powers. As another interesting example of the use of a linear recursion, we consider the problem of raising a number x to an arbitrary non-negative integer n. That is, we wish to compute the power function defined as power x and n equals to x to the power of n. We use the name power of this discussion to differentiate from the built-in function pow that provides such functionality. We will consider the two different recursive formulations for this problem that lead to the algorithm with very different performance. A trivial recursive definition follows from the fact that x to the power of n is equal to x times x to n to the power of n minus 1. Yeah, because you just would sum, that's, okay, got you. You can sum the powers together to, got you. So we break that down to n minus 1. If n is equal to 0, otherwise, we return 1. Otherwise, x times power x n minus 1. Yeah, I got you. Okay. This definition leads to a recursive algorithm shown in code fragment 4.11, where we have def power x. If n is equal to 0, we return 1. Else, we return x times the power of x n minus 1. Computing the power function using trivial recursion. A recursive call to this version of power xn returns in O of n time. Its recursion trace has a structure similar to that of the factorial function, with the parameter decreasing by 1 for each call and constant work performed at each level of n plus 1. Yeah, so the only recursion is happening over the values of n minus 1, but what you're doing to those, well, you're just running a function across them and doing a multiplication on that function value return. So it's constant operations, but in O of n time, constant complexity, right, is the bottleneck. However, there is a much faster way to compute the power function using an alternative definition that employs a squaring technique. Let k equal n over 2 to the floor, denote the floor of the division expressed as n floor division 2 in Python. We consider the expression x to the power of k to the power of 2 when n is even. N to floor divided by 2 is equal to n divided by 2, and therefore, okay, this just got way more complicated out of nowhere. This book just does this. It just will automatically just go crazy for no reason. So, however, there's much faster way. We consider the expression. Okay, so if n equals 0 and x equals 1, we return 1. If n equals greater than 0 and is odd, we will. So this is going to run in what? N log n time? No, log n time, because we're splitting the list in half by even odd. If we were to implement this recursion, making 2 recursive calls to compute power x of n divided by 2 times power x of n divided by 2. A trace of the recursion call would demonstrate O of n calls. We can perform significantly fewer operations by computing power of x floor n divided by 2 as a partial result and then multiplying by itself as an implementation based on this recursive definition in code fragment 4.12. Let's see what happens. So we're defining a function where we have x and we have n. So we compute the value of x to the power of n. If n is equal to 0, we return 1. So if we're raising our power or our value to a power of 0, we return 1. Else, we have a partial variable which we compute the power function. We recursively call the power function on it within itself for the value of x, and then the value that we are powering is the floor divided by 2. It's the floor of divided by 2. Okay, gotcha. So result equals partial times partial if n modulo 2 is equal to 1, meaning it's an odd number. Result multiplied by x and return result. So if it's an even, we would just return result, partial times partial. If it's odd, we would multiply it by x and return the result. Okay, let's see what the recursion trace looks like for this. So we would first start off with, if we want to have 2 to the power of 13, it would then get broken down into 2 to the power of 6, which would then get broken down in 2 to the power of 3, which would then get broken down in 2 to the power of 1, which would then get recurs down to 2 to the power of 0, which we would return 1 in our base case, and then 1 we would return 1. So 1 gets returned. One times 2. So 1 times 1. So we multiply it by itself right here. And then this is an odd number, so we multiply it by x, which is 2. Right? And then we return that value of 2. We multiply it by itself, and then it's even. It'd be 2 to modulo 2 is equal to 1. Actually, expression is incorrect, right? It would be 0. So if our n is we return 2. As result. So our n is still provided as 1 in this case, though. So it's odd until we get to here. Interesting. To analyze the running time of the reversed algorithm, we observe that the exponent in each recursive call of the function power xn is at most half of the preceding exponent. As we saw in the analysis of the binary search, the number of times that we can divide n in half before getting to 1 or less is O log n. Therefore, our new formulation of the power function results in O log n recursive calls, just like we predicted. Each individual activation of the function uses O of 1 operations, including the recursive calls, and so the total number of operations for computing power of x to the power of n is O log n, and this is a significant improvement over the O of n time algorithm. This improvised version also proves significant saving in reducing the memory usage. The first version has a recursive depth of O of n, and therefore O of n activation records, and simultaneously stored in memory. because the recursive depth of the improved version is O log n, the memory usage is O log n as well. Okay. So I'm going to go screenshot. And I'm going to take this guy here. No, I won't. It was too long. We'll delete it and it's all right. Let's just keep moving here. We're making good progress. Okay. How y'all doing today? I hope everyone's doing well on this Saturday morning. It's a quiet chat today. Not a lot of chatter going on. People seem to be waking up here. But we're just going over recursion, getting some examples of linear recursion through swapping elements in a list, powering elements in a list. The example provided above in the example we did on the whiteboard of I believe the ruler was linear recursion, right? Was the ruler? No, this was binary. The ruler was binary. The one that the ruler was binary. We did the one on example, the good Fibonacci was linear because we only call a single good Fibonacci within it. Gotcha. Hey Vash, I appreciate you leaving a message. Thanks so much for coming in this morning. How you doing? All right, let me go ahead and see how we're doing here on stream. Hold on one second, you guys. All right, let's keep moving here. Ooh, too far. Binary recursion. When a function makes two recursive calls, we say that it uses binary recursion. We have already seen several examples of binary recursion, most notably when drawing the English ruler. Exactly, we just talked about that. Or in the bad Fibonacci function of section 4.3. As another implication of binary recursion, let us revisit the problem of summing the n elements in sequence S of numbers. Computing the sum of one or zero elements is trivial. With two or more elements, we can recursively compute the sum of the first half and the sum of the second half and add these sums together. Our implementation of such algorithm in code fragment 4.13 is initially invoked as binary sum of a, 0, length of a. Okay, so binary sum takes in some sequence with a start of 0 and a length of that sequence as a stop. So we would, if the start is greater than or equal to stop, we return 0, meaning that there's 0 elements in this slice. Returns a sum of the numbers in the implicit slice, start, stop, okay. If the start is equal to the stop minus 1, so if the start is 0, the stop would be 1, we return just that sequence, meaning there's only one element in the slice. Got you. Else, we would find a midpoint using a binary recursion. We'd find a midpoint, and we would return binary sum of the sequence mid start plus binary sum sequence mid stop. Oh, start to mid plus mid to stop. Summing the elements. Okay, so you'd cut it in half and sum the halves, and then sum that return that together. Okay. To analyze algorithm binary sum, we consider for simplicity the case where n is a power of 2. Figure 4.13 shows the recursion trace of an execution of binary sum 0 and 8. We show the recursion trace of an execution of binary sum 0 and 8. We label each box with the values of parameters start, stop for the call. And the size of the range is divided in half at each recursive call, and so the depth of the recursion is 1 plus log of 2 log n. Therefore, binary sum uses log n amount of additional space, which is an improvement over O of n space used by the linear sum function. However, the running time of binary sum is O of n, as there are 2n minus 1 function calls requiring constant time. So the space used is log n amount of additional space, but the running time remain in O of n, because you still have to, go over each of those values and sum them together. You're breaking it up into chunks to use less memory. Got you. So you take O of 8, which becomes O to 4, which is summed, which breaks down to 0 and 2, which breaks down to the slice to 2 and 4, which breaks down the slice 0 and 1, and 1 and 2. And then these would all be summed and returned basically as the sum from 0 to 8, which would all be all of these added together. All right, multiple recursion. Generalizing from binary recursion, we define multiple recursion as a process in which a function may make more than 2 recursive calls. Our recursion for analyzing the disk space usage of a file system is an example of multiple recursion, because the number of recursive calls made during one invocation was equal to the number of entries within a given entry of the file system. Another common application for multiple recursion is when we want to enumerate various configurations in order to solve a combinatory puzzle. For example, the following are instances of what is known as summation puzzles. Pot plus pan equals bib, dog plus cat equals pig, boy plus girl equals baby. To solve such a puzzle, we need to assign unique digits, that is 0, 1, all the way to 9, to each letter in the equation in order to make the equation true. Typically, we solve such a puzzle by using our own human observations of a particular puzzle we are trying to solve to eliminate configurations, that is, possible partial assignments of digits to the letters, until we can work through feasible configurations left, testing for the correctness of each one. If the number of possible configurations is not too large, however, we can use a computer to simply enumerate all of the possibilities and test each one without employing any human observations. In addition, such an algorithm can use multiple recursion to work through the configurations in a systematic way. We show pseudocode for such an algorithm in code fragment 4.14. To keep the description general enough to be used with other puzzles, the algorithm enumerates and tests all k-length sequences without repetitions of the elements of a given universe U. We build the sequence of k elements by following the steps: recursively generating the sequence of k minus 1 elements, appending to each sequence an element not already contained in it. Hey, Haunted, I appreciate you coming in and saying hello. Welcome. How you doing? Throughout the execution algorithm, we will set U to keep track of the elements not contained in the current sequence, so that an element E has not been used yet if and only if E is in U. Another way to look at the algorithm in code fragment 4.14 is that it enumerates every possible sized k order subset of U and tests each subset for being possible solution to our puzzle. For summation puzzles of our universe is equal to a set from 0, 1, 2, 3 all the way to 9, and each position in the sequence corresponds to a given letter. For example, the first position could stand for B, and the second could for 0, and the third for Y, and so on. So algorithms puzzle solve takes in some integer k, a sequence S, and a set U. We output and enumerate an enumeration of all k length extensions to S using elements U without repetitions. For each element in U, do the following. Add E to the end of the sequence S. Add the element to the end of the sequence S. Remove E from U. If k is equal to 1, then test whether sequence is configuration to solve that puzzle. Okay. Hello, Theed. Morning. How you guys doing this morning? Yes, good morning. We're hopping into some recursion here in the morning, so it's gonna be a doozy, that's for sure. But I appreciate you guys joining me today. Welcome. In figure 4.14, we show a recursion trace of the call to puzzle solve 3, S, and U, where S is empty and U is a set ABC. During the execution, all the permutations of the three characters are generated and tested. Note that the initial call makes 3 recursive calls, each of which in turn makes 2 more. If we had executed puzzle solve 3 SU on set U consisting of 4 elements, the initial call would have made 4 recursive calls, each of which would have been a trace looking at like the one in figure 4.14. So we solve puzzle solve for a integer k of 3, an empty list, and a set ABC. That gets has a multiple recursion levels of 3, which gets broken down into k minus 1. We remove the first element from okay. So we will remove okay, so it's just creating all the possible anagrams of the or different order of the list, basically, of the set. Okay, cool. All right, we're on 4.5. I think we're almost done with the chapter. Wow. Okay, we have 2 more pages and then we're done with the, no, sorry. 1, 2, 3 more pages and then we are done with recursion. Chapter 4, guys. We finished chapter 4 in like, what, 3 days? 2-3 days? Round of applause. Wow. Obviously, we have a lot of practice and we don't have that much reinforcement problems either. So we might fly through this one pretty easily. So we might want to consider doing some additional studying and just really solidifying these recursion before we move on. It was a shorter chapter. But wow, we're almost done with chapter 4, guys. Good job. Okay, so let's keep moving here. In general, an algorithm that uses recursion type typically has the following form. Test for base cases. Oh, let me go ahead and make a new header here. Michael 1, chapter 4, 0. I just saw Tower of Hanoi Stare. Is that a movie? What is that? Haunted? I don't know what are you talking about? Or show? We begin by testing the base set of base cases. There should be at least one. These base cases should be defined so that every possible chain of recursion call will eventually reach a base case, and the handling of each base case should not use recursion. Recur. If not a base case, we perform one or more recursive calls. This recursive step may involve a test that decides which of several possible recursive calls to make. We should define each possible recursive call so that it makes progress towards a base case, meaning that you need to either increment down or like from down to the base case or to the base case, or you'll get stuck. Um, I just saw Tower of Hanoi stare. It's not. It's a recursive problem. It was in the exercise. Oh, let's go. Tower of Hanoi. Here, yeah. The Tower of Hanoi puzzle. Oh, I've seen some of these puzzles in like in some foreign countries, like in videos I've seen. These are pretty popular in like maybe like is it Asian countries? Yeah, we're gonna get to that one. All right. So we want to reach a base case with our recursions, right? Parameterizing a recursion. To design a recursive algorithm for a given problem, it is useful to think of the different ways we might define subproblems that have the same general structure as the original problem. If one has difficulty finding the repetitive structure needed to design a recursive algorithm, it is sometimes useful to work out the problem on a few concrete examples to see how the subproblem should be defined. A successful recursive design sometimes requires that we redefine the original problem to facilitate similar looking subproblems. Often, this involved reparameterizing the signature of the function. For example, when performing a binary search in a sequence, a natural function signature for a caller would appear as binary search data target. However, in section 4.1.3, we defined our function with calling signature binary search as data target low and high, using the additional parameters to demarcate sublists as the recursion proceeds. This change in parameterization is crucial for binary search. If we had insisted on the cleaner signature binary search data target, the only way to invoke a search on half of the list would be to have make a new list instance with only those elements to send as the first parameter. However, making a copy of the list would take O of n time, negating the whole benefit of the binary search algorithm. If we wish to provide a cleaner public interface to an algorithm like binary search without bothering a user with extra parameters, a standard technique is to make one function for public use with the cleaner interface, such as binary search data target, and then having the body invoke a non-public utility function having the desired recursive parameters. So if you want to make this easier for a user to use, in terms of just like their programs or something, if like it's a package or something, you could provide just a binary search with a data, which the user can just provide the data set and the target, but then you could have that load in on the back end into another function that actually would, have these highs and lows parameters, which are essential, right, for binary search. We have to have the high and low parameterization to then divide that high and find the average, the midpoint between the high and low, divide that, use that to create, a high-low check on our value target, and then basically having our list in each time creating that log n effect of time complexity. If we wish to provide a cleaner, okay, got you. You will see similarly parameterize the. You will see that we similarly reparameterize the recursion in several other examples of this chapter. Reverse, linear sum, binary sum. We saw a different approach to redefining a recursion in good Fibonacci implementation by intentionally strengthening the expectation of what is returned, in this case returning a pair of numbers rather than a single number. Gotcha. All right. So we'll say we don't take much notes here. I'll go back through and get some more detailed notes on these sections when we do some problems, but I'm just doing a first general pass here. Designing recursive algorithms, right? So you'll say like one, you'll test for base cases. And then two would be recur, right? And then we'll say like this. We'll say parameterizing a recursion. Oh my gosh, my spelling is bad this morning. Okay, and then we'll put that there. Okay, we'll make some notes. We'll just get some placeholders for those notes. Get those going. Like so. Yeah, like that. And then this will be 4-6. Like I said, guys, we are almost done with this chapter. We are only 2 pages away. Let's get caught up on some chats here. Theed, if after each chapter you solve an exercise from code words like a final challenge, if after each chapter you resolve an exercise from code words like a final challenge, what do you mean, Theed? I'm not familiar with code words. Do you mind explaining? Haunted Abe Abe says, followed on GitHub, I'm subbed 07, gonna go sleep. Have a great Had a group discussion of machine learning today. Went well. Good luck with your studying. Have fun. Thank you so much for the sub and for following along and supporting me. I also have a Discord link below where I have conglomerated all my study resources that I'm using, including this book and all my notes and everything, into the Discord just for easy access. So feel free to join that if you want to, join the community. Um, and have a good sleep. I appreciate you stopping in. Thank you. Wasil, live early with it. Yes, we are. We are doing an early stream this today. Being productive, getting out of bed, and getting learning right off the jump. I have an event later this afternoon, so I have to leave and drive to about an hour and a half away. But I'm gonna try to come back and stream later tonight. So I'll try to do a double feature. Hey Joe R123. Hey bro, how long have you been coding in Python? I appreciate you coming and leaving a message. Thanks so much for joining me. I have been coding in Python for about 6-7 months now. I started at the end of June 2024. The end of May of 2024, beginning of June. I have a Bachelor of Science in Human Biology and a minor in Chemistry. I work as a formulation chemist at a biotech company where I make a lot of biological controls used in patient testing and diagnostics, like in hospitals and clinical settings. I wanted to further improve my skill sets in just data science and data analytics and analyzing, things in general. And so I wanted to learn how to program and code and use computers to make my job easier on the back end. And so I started with Harvard CS50P at the beginning of June 2024. I completed that very part-time over the course of the summer 2024. And so this past August, I submitted my final project, and it really sparked a drive to want to learn more and keep going. And so I created the channel back in August as well to document my progress as kind of like a video journal, as well as create a community of people in a similar situation as myself who might want to have, might want to have additional resources, companionship, network together, things along those lines. So, and it's also a way for me to have these concepts be solidified. I have to go back and edit these videos, watch the streams, interact with the Discord. It's all very fun, but it also helps to solidify these concepts just even further, just by the sheer amount of time being spent thinking about them and discussing them. So it definitely has, I'd say, drastically improved the rate at which I'm learning. I've had a lot of people come into the chat over the past couple of weeks saying like, "Wow, you're really improving quite fast." So I hopefully that this method that we're doing is working, and that we are learning these concepts at a rate that is somewhat sustainable. And obviously, we don't want to go too fast because we don't want to have gaps in our knowledge. This is all independent, right? So there's no point in moving on. We don't have an exam at the end of this that we're trying to crunch and grind for because we just have to do it in that amount of time. No, 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 no. This is all independent. By moving on and having gaps in our knowledge only will hurt ourselves later on down the line. So we're not moving on unless we know things. So even though we're coming to the end of recursion, we're going to do some practice problems. And if I still am struggling, I'm going to stay on it for a couple more days to solidify it before we move on. But I'm starting to pick up things pretty good here on recursion. It's looking, I'm starting to understand it while I draw it out and stuff. So, yeah. Wasil says, how many chapters in this book and what book is it? Yeah, this is the Data Structures and Algorithms in Python book. This is a collegiate level data DSA book. At least I would think so. It's pretty hard and challenging. It goes over all of the big O notation functions in chapter 3. Big chapter 4 is in recursion. The earlier chapters 1 and 2 were just Python review and classes and object orientation. And so it's really going to dive into here about all the ins and outs of DSA and Python more specifically. I provide a copy of this PDF in my Discord just as a resource for you guys if you want to access it yourselves, or you can just look it up online. I think that you can also find it like I did there. Joe says, so Code Ward is like LeetCode. Basically, you can practice your coding ability. You can pick and choose what topics you want to test out. That'd be a good idea, actually, at the end of every chapter that we do, maybe to go do a couple of practice problems for maybe LeetCode or Code Wars to solidify them. So we'll give that a go, actually, for this chapter. Thanks for the suggestion. I appreciate that. Your channel was recommended me a few days ago. Well, that's great. That's exactly what I'm looking for. I'm so happy we were able to connect here, and I appreciate you following along. Thank you so much. All right, let's keep moving here. So this is eliminating tail recursion. The main benefit of a recursion approach to algorithm design is that it allows us to I don't know how to pronounce this word. I'm gonna be honest, I don't think I've ever seen this word in my English existence. Is that sad? I've never seen this word before. Succinctly? What? Define. Define the succinctly means expressing something in clear and concise how pronounce. Succinctly. Oh, subsequently. Oh my gosh. Oh my gosh. I'm so dumb sometimes. For how fast I can picking up on this algorithm stuff, sometimes I can be real bonehead. Subsequently. Subsequently, yeah. Take advantage of a repetitive structure present in many problems. By making our algorithm description exploit the repetitive structure in a recursive way. Sorry, let's back up. The main benefit of a recursive approach to algorithm design is that it allows us to subsequently. I don't even know if I'm pronouncing that right. Wing Hong, oh, my other account is shadow banned. Hi there. What do you mean shadow banned? I haven't. What do you mean? I haven't. Hopefully that wasn't referring to me. I haven't I haven't banned anyone from the chat or anything. So if I did on accident, let me know. I'm not sure what you mean though. Joe says, "Oh wow, having a science-based degree is great. Computer science as program can intersect with biology and similar fields. I don't know if you have heard of computational biology." Yeah, I honestly I don't know too much about how they intertwine. I have a very broad and specialized knowledge in the physical aspect of the science and chemistry of human biology and things. I specialized in like the lab. I work in a lab. I specialize in handling chemicals, managing and stuff. So I would really like to actually get into like the data science of it behind the scenes in computational biology, exactly like you say. I don't know too much about it. I've heard about it, but do you have any like resources or things that you would like to share about that information? I would be more than willing to listen. Wen Hong says, I'm doing graphs on code signal for Python. Awesome, that sounds great. What is code signal? Is it another kind of like course or online format? Maybe in the future you can look into this field. Yeah, definitely need to check that out. My third week on Python tutorials. Oh, great. That sounds great. If you're still learning Python, I highly, highly, highly recommend. On the channel, we read aloud, just like we're doing for the data structures and algorithms book on the right side of my screen. We read aloud the Python crash course book, which gave a general how to use, and obviously as in the title, a crash course of Python in part one of the book. We read all of the part one live on stream and did all of the try it yourself problems live on stream, completed all of those, and got a lot of really solid hands-on practice with this book. Super proud that we were able to complete that. We also have something to look forward to, Fluent Python we will get into eventually, and then we also will get into Python machine learning, but we are just getting into DSA and Python right now, and so we will get into those soon enough. But I highly recommend doing the Harvard CS50P course online and then pairing that with the Python crash course. Those two resources together, hand in hand, will pretty much set you up for success with all of the fundamentals of Python, in my opinion. I've been using Python for postdoc physics works and never did any DSA and realized it's very different versus generic science/physics use. We use a lot of built-ins and a tons of brute force. Oh, nice book. I will look into it. Thanks. Yeah. Feel free. I have a Discord link below where I have just conglomerated all of my study resources into one location. For example, all of the books that I'm using, I provide PDF copies of them within the Discord. I have my own personal notes. I have, sharing of my projects. I have just a communication forms for asking help, things like that. So join the Discord below, completely free for everybody, just to come together and, help each other out and provide. I wanted you guys to have the physical resources that I'm doing on stream here. And thanks so much for joining the channel, Wen Hong. I appreciate you coming in and being so and participating. Okay. By making our algorithm description exploit the repetitive structure in a recursive way, we can often avoid complex case analysis and nested loops. This approach can lead to more readable algorithm descriptions while still being quite efficient. However, the usefulness of recursion comes at a modest cost. In particular, the Python interpreter must maintain activation records that keep track of the state of each nested call. When the computer memory is at a premium, it is useful in some cases to be able to derive non-recursive algorithms from recursive ones. In general, we can use the stack data structure, which we will introduce in section 6.1, to convert a recursive algorithm to a non-recursive algorithm by maintaining the nesting of the recursive structure ourselves, rather than relying on the interpreter to do so. Although this only shifts the memory usage from the interpreter to our stack, we may be able to reduce the memory usage by storing only the minimal information necessary. So this talks about some sort of memory handling in a thing called a stack, but we're going to get introduced to that into a later chapter, so I'm not going to really worry about that right now. Even better, some forms of recursion can be eliminated without any use of auxiliary memory. A notable such form is known as a tail recursion. How do I want to do this? Look like this, which is tail recursion, right? And I'll just make these bold, whatever. Tail recursion. A recursion is a tail recursion if any recursion call that is made from one context is the very last operation in that context, with the return value of the recursive call, if any, immediate returned by the enclosing recursion. Define tail recursion. Tail recursion is a type of recursion where the recursive call is the last operation in the function. In other words, the function returns the result of the recursive call directly without any additional computation after it. This allows for optimization by the compiler or interpreter, converting the recursion into a loop, reducing the risk of stack overflow. So you return, in this example, factorial is a tail recursive because the recursive call in the last action and no further computations occur after it. Okay. Okay, I'll copy this over, paste this right here. Oop. You guys hear that wind? That's wind outside. That's wind banging against my window and wall. It's really windy here in the Bay today. Sorry. Wing Hong says, "Oh, nice book. Wow, I made a quote political reference and YouTube blocked it from appearing here. Oh, interesting. I just explained why it was shadow banned, and there was a sentence contains searchable ban terms, so YouTube auto blocks. It's a benign term. Oh, interesting. Interesting. Sorry that happened, Wing Hong. I don't have any like words or anything like, you know, flagged for removal or something on my stream, so it wasn't on my end. So think of a stack as a pile of plates stacked upon each other. You can't stack a plate from the middle because you will drop all the other plates. Instead, you need to pick from the top. Oh, okay. And so do you want to limit how high your stack gets? Like the higher it gets, does the more, obviously, is that where stack overflow comes in? Of the recursive functions demonstrated in this chapter, the binary search function in code fragment 4.3 and the reverse function in code fragment 4.1 are examples of tail recursion. Several other of our linear recursions are almost like tail recursion, but not technically so. For example, our factorial function is not a tail. It's not a tail recursion. It concludes with the command return n times factorial. This is not a tail recursion because an additional multiplication is performed after the recursive call is completed. For similar reasons, the linear sum function of code fragment 4.9 of the good Fibonacci function of code fragment 4.7 and the good Fibonacci fragment fail to be tail recursions as well. Any tail recursion can be implemented non-recursively by the enclosed body in the loop for repetition and replacing the recursive call. Any tail recursion can be implemented non-recursively by enclosing the body in a loop for repetition and replacing a recursive call with new parameters by reassignment of the existing parameters of those values. Okay, so instead of like hold on. As a tangible example, our binary search function can be re-implemented as shown in code fragment 4.15. We initialize variables low and high just prior to our while loop to represent the full extent of the sequence. Then, during each pass of the loop, we either find the target or we narrow the range of the candidate sequence. Where we made the recursive binary search call in the original version, we simply replace high equals mid minus 1 in our new version and then continue to the next iteration of the loop. Okay, so rather than using recursion, they're just replacing it with a loop here to do the same thing. In our original base case condition, low is greater than high has simply been replaced by the outside loop condition while low is less than or equal to high. In our new implementation, we return false to designate a failed search if the while loop ends, that is, without having returned true from within. We can similarly develop a non-recursive implementation of the original recursive reverse method of code fragment 4.1. So you add this while loop here instead of calling the recursive of reverse iteration as. In this new version, we update the value start and stop during each pass of the loop, exiting once we reach the case of having one or less elements in the range. Many other linear recursions can be expressed quite efficiently with iteration, even if they are not formally tail recursions. For example, there are trivial non-recursive implementations for computing factorials, summing elements for sequence, or computing Fibonacci numbers efficiently. In fact, our implementation of the Fibonacci generator from section 1.8 produces each subsequent value in O of 1 time, and thus takes O of n time to generate the nth entry in the series. All right, let's get caught up on some chats here. Wow, it's really windy. So the last plate added on the top would also be the first one out if you wanted to remove a plate. How are stacks different from queues? Stacks are last in, first out, which versus queues, which are first in, first out. Stack Overflow is a website like Reddit where programmers go to ask questions. Yeah, you're right, Hong. Think of these words in real life examples. When thinking of a queue, you would want a long queue at a checkout till. Similarly with a stack of plates. Yeah, so a queue would be first in, first out, or FIFO, right? FIFO, where the first value in is the first one in, like a line. Whereas a stack would be you would take from the most recently added item, right? Exactly. Cool. All right, you guys, this was the end of chapter 4. Very nice. So we have 8 reinforcement problems here that we're going to practice with. I'm going to give these a go when I open up the next stream. I unfortunately have to head out here in a little bit for an event I have later this afternoon. So if you're watching right now, please follow along to the stream. I will hopefully I'll be trying my best to do a double feature today, where I will be coming back from this thing I have going on this afternoon, and I'll stream again later tonight, probably around 7 or 8 p.m. PST. So please consider staying for that. And obviously, but you can also follow the Discord link below for announcements when I go live and streaming, as also for all my resources and everything. But yeah, this was the end of chapter 4 here. So we're on page 180. We have read 180 pages aloud here. So we are really putting in a lot of work. Let me tell you, my voice gets tired after a while. I want to kind of read one of these to see what it's like. So describe a recursive algorithm for finding the maximum element in a sequence S of n elements. What is your running time and space usage? Interesting. So I think for these ones, we're actually let's try to actually make the algorithms and code them out. Let's give it a go. So that'll be fun to get some practice with these later tonight when we give these a go. How many chapters are left? I don't really want to think about that. Unfortunately, this book is really long. We're on page 202 of 770. So now, obviously, this book has a lot of like an index that has like a glossary. So all those pages don't count, but we probably have a good 500 pages of content we have to read, and we're only done with about 200 right now. So we got a ways to go. Like I said in my other stream yesterday, I asked for some opinions of, I know that I've been saying I like to start projects and then finish them. I don't want to start too many projects, but I also don't want to have things become too monotonous where I don't want to be too monotonous where things are getting kind of repetitive. So if we feel that we want to maybe take a stop on DSA for a second and jump into more actually Python specific focus of learning the language more in depth into a more intermediate and advanced level, we can definitely take a stab at transitioning into a couple of chapters into fluent Python. But just please let me know, guys, if it gets monotonous. But I also know that DSA is just an extremely hot topic right now, as it's just used vastly in the industry. So a lot of people are enjoying actually learning the DSA, but on the other hand, maybe it's getting kind of old at the same time. So please let me know what your opinions on that. I think there's like up to like 12 or 14 chapters in this book. YOLO, thanks so much for joining. I appreciate you coming in the stream and leaving a message. Thanks so much for participating. I appreciate you coming in and following along. Thank you. Um, that's really good progress. Just think just double and you are almost done. Exactly. So we've been going on this for about a week and a half, 2 weeks now. So maybe it's another week and a half, 2 weeks, and we're going to be done with this book if we just keep going at the pace we're going. So, that is another a little side effect. If we do stop and transition into maybe starting another book or doing something, it's just going to take longer for us to finish this book actually. So that is a trade-off. So just let me know what you guys would prefer, or if you guys just kind of like what we're doing and just the method of finishing things. But I will also like to add on the back half of my streams, you guys, apart from my learning, I do implement and try to create independent and personal projects. So right now, as a stream, in the past we wrote as a stream the task tracker application, which was a basic program. It's quite small, not too small, but it's a smaller program that actually reads, save, and writes files and reads files and creates tasks, and you can manage those tasks and rank them and view them, and it's a great little CLI program. You can check out the video I posted on my channel giving a demo of this just recently. It's my most recent upload, or you can check this out on GitHub and have this program for yourself, and manage your tasks and have a task manager for you. We wrote this live on stream, like I said, so in the back half of my streams, I implement what I'm learning in these books into actual projects to solidify those learnings and actually apply them. So right now we are writing and working on a project called the Small Business Manager. And last night what we did is we worked on this big chunk of code here. We wrote all of this last night. If you weren't here for that part, feel free to check that out. We were not successful, although it was our first attempt at ever trying to write a binary search algorithm for our for our small business manager. So, right, we needed to know these algorithms because our users were going to have upwards of hundreds of thousands of items potentially within their inventory systems, and they need to be able to access them and convert them into sales and then manage that sales information appropriately. So we learned about the binary search algorithm yesterday, and we're like, okay, well, that's a perfect way that we can try to implement this into our actual our program here. So we actually gave it a shot. The only thing that's difficult is I'm separating my object instances, right? My inventory items as items just in storage, or in inventory, a for sale item, meaning that it's listed to the public, and then a sold item, meaning that it has been transacted and sold. And each of these are being stored in their own list accordingly, and I'm transitioning those items out of those lists and into others as they transition from phase to phase. So I was having to do a triple binary search across all three of those lists. So that's what was giving me some trouble, is I was trying to figure out a way to have the user be able to flag a value, because I was having to have I was having a low, right? But for binary search you have to have a low and a high. And so I had a low value, but I was having to have a high for the items list, a high for the for sale items list, and a high for the sold items list, and then running a triple binary search across all of those parameters, thus having a binary search, 3 log n binary search, just reduced down to a log n, O log n time complexity with a constant factor of 3. Now, it would definitely be fast and do what we want, but I failed yesterday. Now fail is a harsh word. I was just unsuccessful at actually implementing it. We got really, really close, but we're going to give this another go tonight as well. Try to implement. We have a linear search here, right? We have a find by item number function here where we just linearly will search through and all of the values in each of these category lists, but that could take a while if we have a lot of items. So what we do is I ran this, I tried to get a binary search going, to drastically improve the speed of this function. Right. Wow, very nice. When I worked in the industry long ago, all data was managed with SQL database. Are things very different now and how data is handled? It seems like Python is keeping things without needing a database. Um, yeah, so that's very, I think, standard. I'm not in the industry I am a chemist, so I'm not in, CS industry at the moment, but from what I've heard is SQL still very used. Um, but I just don't have any experience. I haven't learned anything about it yet, but we will get there hopefully. But right now, my data structure is just a dictionary object that has key values associated to each of these objects, and then a list that is returned from the items found within the files when read and loaded. So just to give you guys a quick run here of the program, see, oh, it's not going to let me because I have this binary search function that's not correct yet. So let me go ahead and I'll just command / to comment that section of code out for now. But if I go ahead and run the program here, you can see that I have these menus being created with various functions that I've made, like a create menu function and things like that, similar to the task tracker application. But we have these menus and we can access. Right now we're working on the inventory menu, so we're in one. We have the add item functionality already added, so we can add items. For instance, let's go ahead and add one. Let's do let's say this is a stream test item, right? And then this is the cost is 10. Just so you guys know, I'm not keeping costs in terms of floats. Costs are received in the form of strings or integers, and then depending on their instance, they are converted and split upon their, if they're given in a dollars.cents format, they are split on the period, converted into a total of cents, right, to track whole integers rather than floats, because floats might behave poorly or weirdly on other systems. So we are converting everything from dollars to cents, USD, right, to handle currency. So we'll have 10. So we can say whole integer. We could have said 1050, and it would give us 1,050 cents, or this is just going to give us 1,000 cents. So item size, right? We have to provide a string that's within our size parameters. So we have a function here that requires that you be within the available sizing within our run items function here. So we'll say that the item is a medium. We have provided the user to load in the item so they have to assign a date to the item that it was created on. So they can either use the current date or they can override it using a date in the past. So I'll just say yes for the current date. And let's say now we added this quantity parameter as well, where this will just create a duplication of these attributes for a X integer number of items or N integer number of quantities. So we'll say like 5 here. And then if we go ahead and exit out of the program to where it saves, right, we can go to the items list, and as you can see, those 5 items were created successfully with that add item function. And it is of note that the item number attribute is increased by 1 each time for those new items. So that is not the only thing that's not duplicated within those attributes. Is we do have increasing item numbers to obviously help organize our system. So we have this appropriately being loaded in, and then we can convert these into sold items or into for sale items and yada yada yada. So it's a really cool program we've got going so far. My goal is to eventually get it to be able to obviously convert all of these items and convert them into sales, and then also maybe manage expenses. You can load in expenses, and then using that information create reports that can, for income statements, cost of good reports. You can filter that by months to years. You could have all these different ways to manage your small business rather than, rather than having to use Excel or a paid program like some like a TOS program or a Shopify. This is going to be just a free program for people and just to people, business owners to use, right? Let's get caught up on the chat. Wing Hong says, never quote fail, but just quote not yet completed. Exactly, for the binary search. Uh, Takatu Yogiri, thanks so much for joining. I appreciate you leaving a message. Do you plan on learning Rust? Um, I don't know. I've never heard I've obviously heard of the name. I've never ever seen a line of Rust code, but I wouldn't. I'm always open to learning new things. My current philosophy though is I'm trying to really gain a solid, very solid understanding and foundation in Python in general. Before I move on to other languages, I think that there's a current trend for beginner programmers and new programmers to try to quickly move on and gather languages like gym badges in Pokemon. Like, I know HTML now. I know CSS now. I know Rust. I know Java. Like, but do they really know them deep down to their core? Are they proficient in all of those languages? Most likely not. They're probably proficient in a general sense, but in each one of them, they need more skills and more practice. So that being said, I think my philosophy of really focusing on a specialty in one aspect and then transitioning after you have mastered it is my approach for this. So yeah. But yeah, I will definitely be learning other languages in the future. But for the moment, I'm really just focused on Python and just getting a mastery in this and in computer science in general with using Python as my first instance. Very nice one. Wow, there are almost 500 subscribers. Yeah, I know, right? We just hit 400 like yesterday, like 2 days ago. What? We're almost at 500. It's you guys are really showing me such love and support, and I couldn't be more grateful. And I'm blushing all the time thinking about it. I really my goal was to create a community of beginners, not even only beginners, but any type of programmer at any stage that creates a more friendly environment that can take the stress off of learning. We're not forcing ourselves to learn because we need to make money, we need to have a job. No, we're forcing ourselves to learn because we want to get better individually. We want to improve on a personal level, whether it be for any sort of activity, coding, playing guitar, working out. Like we these should be fun activities. We're not going to spend our time, our valuable time, doing something that we don't enjoy. Like that's just against my philosophy. So, um, Wing Hong says that's incredible progress. Thank you so much. I appreciate the kind words. And yeah, people have been telling me I've been improving quite rapidly. So, just for those that are watching the stream that are wanting to, improve as well, just keep following along. Right here with me. You're learning these concepts with me, talking about them, hearing them. You're going to be picking up on the same material that I am. So, if you're wanting to, follow, not I'm not saying that you have to or you should, but if you're wanting to, follow a similar pathway, consider joining the Discord and doing these similar resources that I'm doing. I'm kind of I'm kind of like the guinea pig in a sense for weeding out some materials that maybe aren't as helpful and showing you that these ones were really helpful and from a beginner's from a raw beginner's point of view. Yeah. Kevox says, oh, hold on. So, Theta said, in no time you could be financially compensated by YouTube in addition to learning. You'd be rewarded for it. Yeah, that'd be great. Someone asked about doing donations yesterday. I said, no, I'm not really interested. I want you guys to use your funds for yourselves and improving your own lives and your things. But if the channel keeps growing, that would definitely happen, and that'd be fantastic. But I'm again, I'm focused on the learning and the learning is the true value in here, as well as the companionship with you viewers on the stream. That's where I'm getting a lot of value from this. What databases are you using to organize? Are you using pure Python? I'm using pure Python right now. All of my items are being stored in a dict object. I'm using classes that store these. We're returning lists that are the values associated with those dict object keys. So right now we're just using all independent Python. We're not having any SQL. I haven't learned any SQL, so I would like to though. I think pure Python for now. I was wondering how Python handles data. It always just stores and retrieves every time the program is ran via SQL database. So the data I'm actually I have file IO handling right now. So I'm not having like a cloud database. Is that what SQL is? It's like a database within like a cloud server. Maybe you have like a API key or something. I'm not sure how it would work, but all of my data is being actually physically written to files on the user's device, and I have scripts that actually, if those files are not found, if we raise a file not found error, we will actually create those files using with open and write mode and write the headers associated for each of those, like for the sold items and the for sold items, they have their different headers and attributes, right? So that's how we're managing data right now, is on file writing. Snapple says learn programming, not programming languages. Exactly. Like I'm not trying to collect languages, I'm trying to collect programming knowledge. So that's exactly the purpose. That's a great way of looking at it. Kavok says, Wings, I have no idea. That's a question I have too. Uh, SQL's data stored on a separate machine. Yeah, oh, interesting. Well, you guys, I have to head out in about a half hour for my event. I got to drive about a half hour. My girlfriend is having a dance recital. She's a dance instructor, and so her students are doing a recital, and I'm gonna go support and be there for that. So I've got about an hour and a half drive. Here. So I'm gonna head to that this afternoon, and then I'm gonna come back and we're gonna take a look at some of the practice problems, reinforcements from the end of chapter 4 here on recursion. We'll give these a stab, maybe try about 3 or 4 of them, and then we will shift focused and start implementing and working on completing our binary search algorithm for finding items by item number, and then we will also start adding in some more features. So if you guys are interested and that sounds something really cool to you, thanks so much for following along and supporting. We're almost at 500 subs on the channel, which is just mind blowing. Can't believe it. We're growing so fast. Join the Discord if you want access to all my study resources and to connect with me personally on offline when I'm not on stream. I replied on the Discord all the time. I'm active on there, and so yeah. And again, you can access things on my GitHub, all those resources.